know a bit about when did this disease occur for the first time. Unfortunately, like I said, it is very difficult to study the evolution because you don't really know how fast those bacterial strains change, how fast do they mutate. Usually when we want to get the molecular clock and we want to calculate how fast do DNA sequences change over time, we use fossil calibration points. However, here we do not have fossil calibration points, so you can only look basically how the bacteria change in the lab, for example, in vitro, and then you can use those rates, but you can actually see that the numbers here have very high confidence interval. So 700 to 8,000 or 2,000 to 28,000 is a very large confidence interval because we really have a hard time to calculate the mutation rate here. But despite the fact that most historians said that the Black Death was caused by Yersinia pestis, so it was actually bubonic plague, some people said it was not bubonic plague. Some people said it was a different disease. And the main reason is that when you go into the historic literature, when you read those old English or old German books, what you can actually see are differences between how plague occurs today and how it is described today and how it was described 660 years ago. First of all, the symptoms are different. So in the modern plague that occurs today, usually you see a single bubo, so one lymphatic knot which is infected, which is usually close to the bite where the flea has actually bitten the individual. But when you then look at the historic depictions of the Black Death, people have a lot of buboes, so all over the body, which looks quite different. First of all, you don't have lymphatic knots all over the body. It looks a bit more like maybe flea bites, but then why would they be so big? Or it could be some maybe other disease. People were not really sure. So there seems to be some difference here in the symptoms. So also you see kind of here you have, for example, hysteria, thirst, headache, vomiting. That's actually things that people don't describe today when people get infected. Another difference is that in the 19th century it occurred in California and it occurred in China. There were the biggest outbreaks in the end of the 19th, beginning of the 20th century. However, it was a very slow transmission rate. So it was not like in the 14th century where it spread rapidly all over the place. It was more slowly basically spreading all over the place, which is kind of interesting because, of course, the infrastructure was much better in the beginning of the 20th century than in the 14th century where people like still riding on horses maybe, whereas then they had trains and maybe early cars. So that was kind of interesting and funny. And we also see that for the Black Death, people think that there was a lot of transmission between people. So this kind of pneumonic plague seems to have occurred quite a lot because otherwise it couldn't have spread so rapidly. And it even occurred in places that didn't have rats, which is a bit kind of interesting. So the only possibility people say could be that it was actually transmitted between people, whereas we have almost no descriptions about this pneumonic plague in the 19th and early 20th century. And another difference is that when it occurs today, usually it's during the colder months, not during the hottest months, whereas in the medieval time it occurred all over the year. So there's no correlation between a certain season where it occurs more or less. What we also see, like I said, in the medieval time, it actually occurred in Norway and in Iceland, which are really cold places that do not have rats, whereas today it's only below 42 degrees latitude. So it's only in southern regions. It's never coming to the north. Which is also a big difference. So this is why some people said maybe it wasn't bubonic plague, maybe it was anthrax. Some people said it was a kind of hemorrhagic fever, such as Ebola, for example, or it was an unknown yet not identified virus or something that has spread. So people basically didn't know what it is. So this is where we started with this project. So first of all, we then wanted to identify what has caused the Black Death. So we wanted to see what pathogen was it, what can we actually find in those people. Then we wanted to see how has it changed, so if we can identify it, how has it evolved, how has it changed over the last 600 or 700 years, and then maybe also try to find genetic explanations for the high mortality. So why did so many people die back in the day? Why don't people die of such a disease anymore today in such high amounts? So how can we do that? Of course, somehow we have to get the DNA. We have to get the genetic information, which is usually the only thing that we have left from the time periods, DNA, that we can actually study, because proteins are usually highly degraded, or if you have proteins, you only have a collagen which is stuck in the bones, but you don't have much soft tissue. So genetic information is basically the only thing that we can really study. But then, of course, if you take a bone, which is 1,000 years old, you have, first of all, some human DNA in this bone from that person that bone once belonged to. Then you have also the pathogen, which is still in there because it was basically, you had blood flow in the bone. So if the pathogen was a blood-borne pathogen, it should also be stuck somewhere in the bone. But what you mostly have is actually environmental DNA, because this bone was in the soil, and it was in the soil for 1,000 years. And in the soil, you have a lot of bacteria and fungi and microorganisms, and they leave, of course, their DNA on the bone. So what you really get out of such a bone is more like a soup of DNA, and most ingredients in that soup have nothing to do with human or pathogen DNA, but they're rather kind of all kind of funky microorganisms. So it's really difficult to actually then get those few fragments of pathogen DNA out. And what people traditionally did, of course, was polymerase chain reaction, so PCR. So you basically amplify small little fragments, and if you get a PCR product, yippee, you have actually found this DNA to be present. But that has several problems. So what people have then usually targeted was this PCP plasmid, a small region here, like 100 to 150 base pair long fragments. And they have then used skeletons from the medieval time, and sometimes they found it. Yes, it was present. But sometimes, like this study here, they tried to replicate the work from another lab. They didn't find it. And then they said, oh, the first lab has actually messed it up. That was all contamination because they did the PCR in the same lab where they have modern DNA of Yersinia pestis, which is, of course, a big problem because we have millions of modern molecules, of course, in modern tissue, but in ancient tissue, there's almost nothing left. So it's easy, really, to pick up contamination. And then, basically, that caused a large discussion. So basically, for the last 15 years, people were discussing back and forth, is it actually present in those bones, or is it all contamination? Is it all an artifact, or is it real? But you have actually a big problem. When you do PCR, you're limited to long fragments because you have to have both primers present on your fragment. You have to have something in between. But if you look at the actual length distribution of fossil DNA that we usually get out of a fossil that can be 20 years old or that can be 20,000 years old, it usually looks like that. The DNA is highly fragmented into usually 50 to 60 base pair long fragments. So it's really short. So we have just a few fragments which are rather long, which is, of course, a problem because with PCR you will not find them. But of course, in the last years, we have seen this revolution of sequencing technologies. We don't have to sequence single fragments anymore. We can actually sequence now millions of fragments. So remember, I hope a lot of you remember this machine. Maybe I'm too old now already, but I hope not. The ABI sequencer, something like 8 years ago, was producing about 100 DNA fragments at a time. That was the machine that was used for the Human Genome Project, which took 13 years and cost something like 2 billion euros. And now we have, of course, much better machines. So kind of 2012 now, the latest technology like Illumina HiSeq machine produces about 1 billion DNA fragments. And usually a human genome now costs something like 3,000 euros. So it's much quicker, much faster, and you can produce much more data. So what we can then do is we can then actually take those samples from the medieval time, like let's say bones or teeth, extract the DNA, turn it into a sequencing library, and then put it into one of those high-throughput sequencing machines, because it produces basically millions or even billions of DNA fragments that we can then study and look at. So we don't have to amplify it, we don't have to PCR amplify it, but we can just simply sequence it. And the advantage here is that we're not limited to the long fragments, but we can actually look at almost the entire length distribution of the DNA fragments. Because in those sequencing libraries, you can have 10 base pair long fragments, 50, 100, there's basically no limitation here. So if we compare PCR to this called direct sequencing with this high throughput sequencing machines, with PCR you have basically the short molecules are not available. It's also extremely wasteful because you have to think we have very little DNA, but if I want to study one piece of the nuclear DNA, I have to put in the entire genome to get this one target molecule amplified, which of course means that I waste most of the DNA, which is really bad. You cannot look at chemical modifications. So if, for example, at the beginning of the actual DNA fragment, you have chemical modifications, you won't see it because the primers are actually over here. And that is different for direct sequencing. You can look at all size fragments. You can immortalize the DNA, which is really great. So basically, you take the DNA from the fossil, you turn it into a sequencing library, and then you carry out a PCR on the adapters that you have stuck to the DNA. So you can make millions of copies. So you can always go back to your stock solution, take an aliquot, do something with it, and then you basically never use up your DNA, which is very precious, of course, for every museum curator that has given us, for example, some bone samples. And what you can also do is you can look at the DNA damage. So you can look at the entire fragment from the original beginning to the original end, which again will become important later on. So what we can then do is we can take the DNA, we can make many, many copies, we can take an aliquot and then put it again into one of those sequencing machines. However, there is still